Okay, thank you. Yes. If I need to mute it, just let me know. Okay. So this is not about k-wargs. There are a couple functions in here, but that's not really the point of the talk. This is exponentiation, and I got like 100 slides, so I'm going to try to run. I'll start off talking kind of slowly, and then I'll sort of increase my rate of speech kind of exponentially. Okay? So here we go. All right, so we start off with the original exponent, right, the square, right? And what they're talking about is areas, right? It's not algebra at all. It's just one square and another square. There's something about the lengths. It all works out, right? It's wonderful. Okay, so when we get up to the 16th century, anybody's Latin, you recognize this? You got about 4 seconds. Shout it out. A cube into 2 cubes and a fourth power into 2 fourth powers in general cannot be done, or anything larger than that. Famous theorem, took 350 years to prove. This fellow came up with it, Andrew Weil. And at those days, they didn't bother with x's and y's. They just spelt everything out. Right. Can you imagine if we had to spell everything out in Python? It might take a little longer. All right. So we've all heard the Zen of Python. What is a zenzazenzazenzazik of pi? Anybody do their homework? It's pi to the 8th. Because zenzazenzik is pi to the 4th, and zenzik is an old word for a square, thanks to Robert Record, The Whetstone of Wit, 1557. Add that to your trivia list. All right, so first computer I used didn't even have multiply or divide built into the firmware. It was all done by subroutines. Amazing, right? No firmware. You had to pay extra if you wanted fast multiplication. All right, so this is what a typical PC looked like back in the 60s. This is 12,000 characters of memory. These disks were about 10 megabytes each, platters like that. And it was the language of mathematics, right? We often think of Python as being a language of mathematics, especially NumPy. Why not? All right, so here's some blah, blah, blah. These slides will be posted, so I'm not going to dwell since we still have 90 to go. All right, so there's a whole discussion here about how exponentiation is to be handled. You'll notice the double star. That's where it comes from, Fortran. Fortran predated Python, and it used the double asterisk. There may have been other languages, but certainly Fortran used it. All right, and there's a lot of rules here having to do with integer values and real values, negative values, exponents of using exponentials with negative values. All right, so let's kind of look through our type scheme in Python. Turns out that Booleans can be exponentiated. Isn't that cool? You can add Booleans, you can multiply Booleans, you can subtract Booleans. It's a little weird when you do. And you can exponentiate Booleans. I don't think you really want to, but you can, all right? So this is where having dynamic types, if you're a big fan of type hints, well, you might be able to save yourself some grief. But otherwise, yeah, you can exponentiate Booleans. All right, and this is what you get. False to the true power is 0. Everything else is 1. Okay, and if you say is it true, of course it'll be true because of how Python handles truth and falsity. All right, so exponentiation, not only is it described by the double asterisk, it also has all these other functions that tie into it in one way or another. So let's just dig right into the math module, right? You import math, and if I get crazed, I may actually try doing some live coding, but let's see how far we get. Okay, So this is a function that was added to Python because of instability when you take e to the x, subtract 1 from it when x is kind of small. Small meaning close to 0. You don't get sufficient accuracy. So here's a new function. Which one do you use? Well, it depends on how close to 0 you are, if you need to know. If you're going to be doing some kind of derivatives, it might be important to know. All right, so here is one way you can calculate exponential functions. It's the old Maclaurin series. And you can see that there's powers of x right here, x squared, x cubed. So when x is really, really small, x squared is going to vanish, x cubed, the kind of thing you do in physics all the time. So that's part of the problem that goes on. Now, the algorithms that are actually used to calculate exponentials are going to be tuned for speed and accuracy, and there'll be some sort of trade-off. It'll vary. All right, so thank you for asking. Here's the CPython implementation detail. Future reading. Another thing, exponentiation shows up in all sorts of interesting places. So when you have modular arithmetic, our friend 7% 2 being equal to 1, right? Modular arithmetic is very, very important for cryptography. It's crazy important for cryptography, right? Every time you use your credit card, right? We want to sort of munge up numbers. And we like it to be primes because primes have nice behaviors. Okay, so here we have exponentiation in some sort of finite field. And it's also involved in the Chinese remainder theorem and one of the classic solutions that came up in the 50s. And here's a little comment here that even though it takes 2 exponentiations, each is more efficient because the moduli are small. Right? All sorts of things you have to worry about before breakfast. All right, so not only do we need to store and calculate, we need to display and input large and small numbers. So we have this E or G formats, and here you go. You need to be a bit of a lawyer to work through this in terms of what you're going to get reliably. You can experiment, easy enough. And we have the data model. So the data model has integers, right? And we have the illusion of an infinite string of bits for integers, right? Our integers can be really, really, really long, and it's really cool that they can be. Okay, so here's something else from the data model. There is no reason to complement the language with 2 kinds of floating point numbers. I think we all agree that, float and double are kind of a nuisance. So of course, what do we have in Python 2? Oh, so we don't have any half floats or mini floats. There's all sorts of IEEE stuff out there about different ways you can represent floating point numbers for efficiency considerations, especially if you're doing some embedded software or have some compute limitations. You might care about it. But we do have 2 types of integers in Python 2 at any rate. And we have the kind of curious effect that they're the same, but they're not really the same, right? Okay, and this is, you don't have to get very big, just 2 to the 100th, and you get a long int in Python 2. Python 3 kind of made that go away quite nicely, unless you have code that kind of depends on knowing that. So get rid of that code or fix it. Okay, so we have all sorts of places we can look at, and we're only going to be able to touch on a few of them. So here's what happens when you take 2 to the 1023. 1023 is 2 to the 10th minus 1. So you can see the internal representation of a 2 to the 10th might somehow have an exponent there that's 10 bits long, somewhere or other, something like that. Okay, when I try to convert this to a float, it's perfectly happy, right? Here we go. It's a nice long number, 1023, 1024. When I try to do it as a float, I can have integers larger than floats in Python, which is kind of counterintuitive. What was the whole point of floating point numbers? It was so you could have really large magnitude numbers, right? Well, you can have larger magnitude numbers which are integers than you can in floats. You just have a memory penalty on that, a huge memory penalty, too large to convert. And if you push the boundaries, you run into all sorts of problems as you get towards these large numbers. And if you're doing lots of computes, if you're trying to do combinatorial problems with lots of factorials, it's easy to get really, really huge numbers. And when you try dividing them, all sorts of nasty stuff happens. All right, so speaking of factorials or exponents in general, right, what's an exponent? It's multiplying, 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 right? That's the traditional view, right? N times for x to the n. Well, what happens when n gets kind of large? And you have this really brain-dead recursive function here, right? Kind of like a factorial, but we're going to just do it for multiplication. Boom, right? Now, it turns out that in Python 2 and Python 3, these recursion limits are slightly different. Okay, you can actually go a little bit further in Python 2 than you can in Python 3. But it doesn't really help because you're going to be dead anyway, right? And recursion is bad for all sorts of other reasons, such as it generates this huge stack of stuff it has to work through and then unwind. And it's slow. It's really quite slow. Speaking of which, let me do a time check, okay? All right, so if you're good on your microseconds and nanoseconds, you can go through all that. Now, we got some interesting edge cases, right? With addition, multiplication, subtraction, you don't really have much in the way of edge cases, right? That's certainly not in the middle of the number series. But with exponentiation, oh yeah. First of all, if we take 1 to any power, what do you get? You get 1, right? Why multiply it a zillion times? Why do anything, right? So you check for the special edge case, 1, right? Now you're going to be having any random number. So every time you check to see if it's 1, you're paying a penalty for doing the check. So maybe not such a good idea. But if you do know what your numbers are, especially if you're dealing, say, with a small finite field, then it might be worth checking. Okay, 0 to any power, let's say any positive power, that's going to give you 0. 0 to the 0, that's going to be a problem, okay? Right, so depending on what your domain is, whether or not you're working with integers or floats or rational numbers, right? You may want to kind of keep track of rational numbers are particularly messy because now you have 2 sets of integers, right? I'm talking about the rationals module, right? Okay, now one thing that's kind of interesting to do, and I wish we could do a bit more of it because I'd like to understand it myself, is how the disk module functions. All right, so let's just see what it does here. Those are, I didn't even bother returning anything. I'm just doing some calc in here. And now I do dis.dis, and I see binary power here. I see AB, and then I see load this constant. All these are constants, but some of these, right here, you can see sometimes it calculates it. Getting towards the limit of what we can have for a decimal. And we have this very kind of funny number here, but of course it comes from the leading digits right here. Okay. So we do have something built in called binary power. All right. So when you're doing numerical work, what are you going to do? You're going to go to a numerical engine more likely. Sooner or later, right? You're going to have to go to NumPy, right? Because the NumPy folks, they put in the effort to make things fast, right? To make it competitive, right? For scientific and financial use, right? And who knows what else? You know, graphics use, right? There are all sorts of places numerical work comes in. All right, so we have all these arrays, and you can actually take the entire, you have a power function here, and you have your own square root function, and you can even do matrix power if you want, matrix squarings, all sorts of very cool stuff, and all sorts of rules here. And then we have SciPy, right? That's the next piece of the food chain as you go into SciPy, and there we have all sorts of things. Now remember our expm1 function. We have that. We also have log 1p, and we have log 2 and log 10. And all these functions, log and exponents, right, they're just mirror images of each other, more or less. All right, so factorials, right, n times n minus 1 times n minus 2, down to 1. Well, that, not only is that not good to do recursively for a number of reasons, it has a good approximation called Stirling's formula. And right in the middle of Stirling's formula is, here's the constant here, square root of 2 pi. There's n, simple multiplication, square root of it. And then we have n over e, where e is Napier's constant, 2.71, So n divided by e to the nth power. So if you're going to be doing a lot of factorials, maybe you want to have a fast and reliable way of doing exponentiation. Okay. All right, so one thing you might be interested in doing is caching your results. Because if it's expensive, why not just sort of store them away? If you're going to be doing 2 to the 10th or 2 to the 10,000th a lot, right? Python does a little bit of this for you, right, in terms of keeping track of values that are being reused, up to garbage collection. But you may want to just sort of have a ready table out there if you're going to be doing predictable exponentiations, right? Good luck. All right. Now, once you get outside of Python, and I mean outside of this kind of abstract language down to the hardware, and you're pushing these numbers around, you have to worry about all these different types of precisions, right, for representing your big numbers. Because exponentiation and representation of exponents kind of go hand in hand, right? We get 10 to some huge power, and you got to be able to keep track of it. So let's see, let's keep going. Now, Fibonacci sequences, right? Rabbits, right? Multiplication of rabbits, right? Classic, nice recursive problem. Oh boy, that goes up exponentially, right? Double exponentially. It really grows fast if you try doing it recursively. Well, it turns out you have a nice kind of closed form that you can use. Okay, and that is phi or phi raised to the nth power divided by root 5. So there you have a nice exponential solution to the Fibonacci. Why calculate it at all if you need the large numbers? Why calculate it recursively? Oh, it'd take forever. Just use the exponential. And this might be a good case for caching, say the first million Fibonacci numbers, right? You calculate them once, yes, maybe, no. Either that or you use the exponentials. All right, so let's look at a classic mathematical problem. When does x to the y equal y to the x? Well, for integers, it turns out for x and y being different, there's only really one solution for positive integers, and that's 2 and 4, 4 squared. And you can do a little bit of work to prove that to yourself, but it can be done. This kind of begs the question as to how we might do this symbolically, right? Because this is like kind of symbolic formula right here. These are what the rational solutions have to look like, right? I have a reference here somewhere or other. And so SymPy, fractions and decimal, are all ways to approach working with exponentials for of rational numbers, right? And here we're looking at integer exponents. All right. Okay, let's move over to square roots for a while, okay? It's kind of a random walk through exponentials because it's kind of like a big field. Okay, So you would think taking a square root is a fairly trivial kind of problem. It is and it isn't. Part of the problem is that sometimes you run into overflow and underflow circumstances. Remember 10 to the 308th, 10 to the minus 308th? That's kind of where Python gets unhappy. And if you have triangles that either have really small sides or really big sides, because, you know, what are you doing? You're looking for distance formulas. And if you really need to calculate the distance, the result is acceptable, but you can't get to it. You can't get there from here. So that's why the hypot function exists, to let you do just that. Okay, because, you know, when we square a number to the minus 200th power, we're going to get 0. Not to the minus 400th, you'll just get 0. So it'll be a hidden underflow. If you try a number to the plus 204th power, yeah, you'll get an overflow. Okay. All right. Let's keep running. So there's some timing there. All right. What about doing logarithms, right? Well, if you have an integer and it's in binary representation, you want to get log 2 of it, all you have to do is count the bits, right? That's all you have to do. So if you have a way of getting to the bit representation of the integer, that's going to be aesthetically more satisfying than going through some sort of numerical calculation to do it. Will it work? Well, kind of. Look at this, right? If I look at the log 2 of x, whatever x is, this huge number here, and I look at the bit length, it's not bad. It's not bad. It works pretty well. Okay, so let's see. Oh, stuff here. Oh, when we get really close to 0, we may want to denormalize numbers, okay, because that's a way of kind of pushing the boundaries. It gives you just a little more edge there. Is it worth the effort? Well, it kind of depends on where you are. All right, so here's some formal definitions of exponents. This is typically what you see for them. So Python does have this nice library that gives you a way of portably expressing the internal representation of a float, right? Maybe you don't want to use JSON for everything. Maybe you just want to push binary around, okay? So here's a way you can use with the FRS function. Okay, there we go, that one. All right, so what do we have inside of this math function, this math module? Well, we have this power function right here. Some blah, blah, blah there. You notice there's a difference between math.pow and just the ordinary pow functions. This will always go to floats. This will keep it as integers. So you need to know which one you're using and why you're using it. Okay, gamma function. So here we have a plot of the gamma function versus the factorial function. You can see that it matches fairly well, even at small values, so it may be worth doing. Okay, so what else uses exponentials? Well, all these hyperbolic functions, including this one here, tanh, which is used in machine learning as an activation function. Whoop, okay, we got to run. Okay. Polynomials, matrices, fractions. Fractions and decimals are really nice modules to look at. Unfortunately, they give different answers to 0 to the 0 power. But beyond that, they're very cool. Oh, you may need to clamp numbers in order to keep the exponent within range. You just move the decimal point, another trick. Boom, 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 boom. Here we go. I think we have sort of a grand finale here. Oh yeah, the Gelfond-Schneider Theorem, right? So you have 2 to the 2 to the 2 power. It should give you 2. Well, not quite. You know, this is a classic numerical issue right there. Okay, now we got SymPy. 3 more slides. SymPy is a very, very cool package. It's fun to play with. Unfortunately, it can be brought to its knees by giving it formulas like this. Remember the x to the y solutions? I want to try to find them. And we can see, it gets unhappy, right? It runs into all sorts of problems. And but it is cool. Boom, boom. Oh, that's it. I want to thank my timekeeper for doing an excellent job with the 1 minute kind of. All right, any comments? Any true stories you'd like to share? I think we have 3 or 4 minutes.
Yeah.
Yes, no? Anybody ever do an exponentiation? No? You should do it, it's fun. Oh, you know what's always lots of fun to do? Well, I'm seeing if anybody, go into Python and just do oh, great. Let me just find a Python window that's open. To the $100,000.
Oh.
Yep, go ahead.
Hello.
Mm-hmm.
Would you recommend doing your calculus homework using a Python library?
I'm sorry?
Would you recommend doing your calculus homework using a Python library?
No, you should use somebody else's Python library because it probably is correct.
So whose Python library might I want to use?
Oh, to do your calculus homework?
Yeah. Because all the problems are just one line of code, right?
Yeah, more or less. I usually go to Wolfram Alpha, to be honest, if I have calculus to do. Because it'll just walk you through the steps. And there's your solution right there. Right. Okay, I'm
Time
just
for
going
one more
to
question or two.
take 2 to a very large power. Let me see if I can change this. And you will find the joy of locking your own, chewing up all your memory. Because Python is going to use all your memory. And it may do so in such a way that you'll have to go out and open up another window and do a little bit of Linux work, do a PS, and go kill your own process. You can try to kill it because it's chewing up all the resources and all the memory. So just sort of a nice little bug to put into somebody's code if they have exponential going on in there. Just sort of like as integers. As a float, it'll do just fine. Are we out of time?
We're good. We still have 1 more minute.
1 more minute.
You have something?
Anybody with a homework problem they'd like to? Yes.
So if we wanted to do this thing with Python, which library should be the?
Well, it depends on what you want to do. Okay. I mean, start with the math library, then go to NumPy.
Yeah. So which one is has the most?
Well, decimal fractions with an S at the end, I believe, and SymPy all have different strengths. So if you're doing pure numeric work, you use NumPy, use Numba, right? So you can really compute. You may even want to go with multiple threads, right, and do something depending on the type of work you do. If you need really super precision, decimals is good. Right? It's more of interest for the financial community, but it has this nice side effect of that you can do quite a bit with it. And fractions will let you keep numerator and denominator if you're wanting to do some theoretical work. Like this x to the y equals y to the x, and try to figure out where that has solutions. We done?
Yes, that's all the time.
Okay.
Thanks very much, Anne.
Thank you. And these slides should be posted whenever they get posted, right?